Okay students, so welcome to the second part of this week's lecture, and this part is focused on the probability of error and comparing the error performance of different modulation schemes. So in this part of the lecture we will be basically looking at first of all the two types of detection, coherent and non-coherent detection and their differences, and then we will do a comparison of bit error performance for various modulation types. And finally, we will be looking at memory signaling and its error performance. So these constitute the main themes of this part of the lecture. With relevance to that, the learning outcomes for this part of the lecture are that the students should be able to first of all understand the detection problem, then they should be able to differentiate between coherent and non-coherent detection. They should be able to compare the error performance of various modulation schemes, and finally they should recognize that EP by naught is not the only performance comparison parameter for memory signaling techniques. So coming over to detection techniques, basically there are two main types of detection. One is called coherent detection and the other is called non-coherent detection. And the primary difference between these two is the presence or the absence of phase recovery circuit. So what is a phase recovery circuit? A phase recovery circuit is used to have a local generated carrier wave at the receiver synchronized with the oscillator at the transmitter. So basically there is some piece of hardware at the receiver which tries to detect the phase of the incoming signal, and the idea is that it wants to match or log the phase of the incoming signal with the local oscillator in order to achieve synchronization with the oscillator at the transmitter. So that's a major difference between these two types of detection. Now in coherent detection, as I've explained, it requires a replica carrier wave of the same frequency and phase at the receiver as exists at the transmitter. Now that is a big challenge. We can say that the local carrier generated at the receiver has to be phase locked with the carrier at the transmitter. So both the oscillators, they need to be synchronized in phase and frequency both. So the received signal and the replica carrier signals, they are cross correlated, and this is something which is also known as synchronous detection. So we will receive a noisy signal and we will try to generate some carrier signals locally, and then we will try some sort of a cross correlation in order to come up with this coherent detection. So you can expect that match filters or their equivalents are used, and because it involves phase matching or phase detection or phase locking, so you can expect some sort of phase lock loops or similar hardware in coherent detection circuits. Coming over to non-coherent detection, the first thing we need to remember is that no attempt is made to determine the actual value of the phase of the incoming signal. That is, phase lock is not the target, so it is not attempted. So it requires no reference carrier for phase lock. Obviously this makes it less complex than coherent detection, but we have to remember that the error probability in non-coherent detection is higher than coherent detection, and so its performance is not as good as coherent detection. But because its hardware is simple, you can expect a well detector or similar hardware in the receiver structure of non-coherent detection. So we have compared both types of detection, and one of them is used, and based on the hardware you can have a guess as which type of detection is being done, whether coherent or non-coherent. Now coming over to comparison of bit error performance for various modulation schemes. So I'm showing you a table here. This table has different values of probability of bit error for different modulation schemes. So these are basically the PB expressions. These are the PB expressions for the best known of the binary modulation schemes, and for PB is equal to 10 to the power minus 4. It can be confirmed that there is approximately a difference of 4 dB between the best and the worst of these schemes that are being shown here in this table. And if you look at these expressions of these values, you can conclude that the best one is coherent PSK, this one, and the worst one is orthogonal FSK, the non-coherent orthogonal FSK, this one. So there is a difference of almost 4 dB in these two schemes. So in some cases, 4 dB is a small price to pay for the implementation simplicity gained in going from coherent PSK to non-coherent FSK. However, in many other cases, even a 1 dB saving is worthwhile. So what you have to remember that there may be other considerations besides PB, system complexity. So for example, if you have a channel with a lot of fading, a non-coherent system may be more desirable or more suitable, because in such situations you might find it hard to establish and maintain a coherent reference between the local oscillator and the transmitter oscillator. So just remember that there might be other considerations. However, when we compare these selected binary modulation schemes based on the expression for probability of error, so we will go for coherent PSK. Now coming over to discussion on memory signaling and performance. First thing that we should be clear about is this curve. It is the curve of probability of error versus EB by N naught, our normalized SNR. So the typical probability of error versus EB by N naught curve will have a waterfall shape. So the probability of bit error characteristics of various binary modulation schemes in AWGN will show a similar shape, a waterfall shape. But what should an ideal PB versus EB by N naught curve look like? So this figure here, that also shows you the ideal curve, ideal characteristic, which is based on the Shannon limit, and this limit represents the threshold EB by N naught, below which the reliable communication cannot be maintained. So we've discussed Shannon already. So based on derivation of Shannon's channel capacity theorem, basically we reached this value of minus 1.6 dB. So we can describe the ideal curve in this figure as follows: that for all the values of EB by N naught above the Shannon limit of minus 1.6 dB, PB is 0. Once EB by N naught is reduced below the Shannon limit, the PB degrades to the worst value of 1 by 2. So it should be clear by comparing the typical PB curve with the ideal one that the large arrow in the figure describes the desired direction of movement to achieve the improved PB performance. As we move along this direction here, that is an improved error performance. As we move along this direction here, that is a degraded error performance. Okay, so let us continue our discussion of memory signaling and performance. And here in this figure, we are looking at different curves. As you can see, bit error probability (PB) on y-axis and V by naught on x-axis. And now inside of one curve, we have multiple curves. So we have the bit error probability for coherent schemes, coherently detected memory orthogonal signaling. So all of them, they are basically different levels of memory orthogonal signaling. And as you can see, as k increases, where m is equal to 2 raised to power k. So k is basically, you can say, the number of bits. So as k increases, the curve, it moves in the direction of improved error performance. Moves in the direction of improved error performance, as you can see here. So it is approaching the ideal curve out of Shannon. So it is going in the direction of improved error performance as k increases. But here in this figure, now that is the curve of PB versus V by naught for coherently detected multiple phase signals. So here we had orthogonal signaling. Here we don't have orthogonal signaling, but multiple phase signaling. And as you can see, as k increases, now we are going in this direction. Basically, as k increases in this curve here, the up arrow, the curve, it moves in the direction of degraded error performance. So now we have a conflict. If you look at this curve for orthogonal signaling, as k increases, we are improving our error performance. But if the signals are non-orthogonal, as k increases, the curve starts to move in the direction of degraded error performance. So, memory signaling, it improves better error performance when we use orthogonal signals, and degraded error performance when we use non-orthogonal multi-phase signaling. So that is what you have to remember. So the question is, why would anyone ever use multiple phase PSK signaling if it provides degraded error performance compared to binary PSK signaling? So as we saw in the previous slide. So if orthogonal is better, just like in BPSK, we have orthogonal signals. Yes, so if you remember the constellation diagram, we have orthogonal signals. So why would anyone prefer multi-PSK if its performance is not good as binary PSK? So what you have to remember that PB by naught is not the only performance criterion. What about the required system bandwidth? So if you compare the performance of these two schemes in terms of bandwidth, what will you say? So for memory orthogonal signals, as k increases, the bandwidth also increases. But for memory multiple phase curves, as k increases, so we can accommodate or we can achieve larger bit rate within the same bandwidth, or if we are keeping the data rate constant, then we need lesser bandwidth. So actually with multiple phase memory signaling, as k increases, the bandwidth requirement decreases. But with memory orthogonal signals, as k increases, the bandwidth requirement increases. So that's where the difference is. So not considering anything else, just CB by naught and bandwidth. So we have a trade-off. We have to make a choice or balance. If you want to go for orthogonal signaling, you will have a better error performance, but we have to compromise on bandwidth because we need a larger bandwidth. So better error performance at the price of larger bandwidth. Or if you want to go for memory multiple phase signaling, you will have a better bandwidth performance, but that will come at the price of degraded error performance. So it's a compromise. if you want to improve one thing, the other thing will have to be compromised. So that's what we have to remember. So in the last, I would like to sum up by discussing the effects of ISI, because in our recent discussion over the last 2 weeks, what we did was that we treated the detection of signals in the presence of AWGN. And if you remember the impulse response equation for Z of t, so even there, if you remember our discussion, we assumed that there was no ISI, so there was no degradation due to ISI. So that was a simplifying assumption, because in practice or in real scenarios, ISI will also be present. So we have studied what ISI does. Yes, ISI can degrade error performance also. If you remember, we compared two curves where in one system increasing the AB by N naught did not improve the error performance, whereas in the other scenario it improved the error performance. So when ISI is present, we will have additional error performance degradation, and that degradation can come in both coherent and non-coherent detection schemes. So what you have to remember that when we are including both noise and ISI, we will have a degraded error performance even further. So that is a subject of research, and